Right. Redundant connection too. This is a very nice problem. There's a lot of things to learn from this one. Basically, we are given a graph. It's a directed graph, and we are given that there is exactly one node which has a zero incoming edge, right? Which means this is the root node. This is where we start traversing. And all the other nodes have exactly one parent. That means they have exactly one incoming edge, correct? I'm saying in terms of incoming edge because that's important for this problem. And then we are given that uh, we are adding one extra edge, one additional directed edge has been added to this tree like structure that I just said, right? So this one extra directed edge can be of three types. It can generate three cases. The first case will be given in the first example. So this is the case. Here we see that 1 is the parent node. It has zero incoming edge. This one is a child node. It has one parent, hence one incoming edge, which is fine. This is valid. This one, on the other case, it has two incoming edges, which means we can remove this and our structure will be valid then, or we can remove this. Which one you should remove? And the question is given whichever comes in the last position, whichever comes after the first one, right? In the vector of edges. So this 2 3 comes later after 1 3. That's why 2 3 is the answer, right? So this is one case. What is the other case? Other case is the second example. Here, if we see this as this one has one incoming edge. This one has one incoming edge. This one has one incoming edge. This one has again one. This one again one. So all of them have one incoming edge, which means the parent node is not decided. What can be the parent node? In that case, we have to detect a cycle. See, there's a cycle. There's always be a cycle because if the parent node have incoming edge, which means there's a cycle, right? And that's why we have to. There's only one option here. We have to remove this edge. Any other edge that we remove, let's see. If we remove this edge, uh, then what happens? This suppose becomes a parent. Then we traverse here, we traverse here, we traverse here, we traverse here. So this is possible. This can be removed, but the problem is 4-1 comes after 2-1. So 4-1 was a valid answer. Sorry, 2-1 was a valid answer, but 4-1 is the one which comes later, and it's also part of the cycle. All right, so um, that's how we are going to solve this. Uh, we have to detect a cycle here, and we have to remove this one, this edge. Now the last case that arises is this one. It's basically, let me just see if I can get that diagram. I can't. Never mind. I'll draw it out. Here, 1, 2, and there is a cycle. 3, 4, 2. We see that there is a cycle, and if we try to count the incoming edges of each node, 0. This is a parent node. It's fine. This is 2. So we see that here we have two edges. This one is again 1, this one is 1. So which are the two nodes? This one and this one are the two nodes or two edges which we can remove. Which one we should remove? And suppose this edge in the vector comes later, right? So if we go with the first example, then we would remove this edge, right? This one comes later, and this one is one of the two edges, which is the reason for 2 in degrees. But that is wrong, because if we remove this, we are just abandoning this node itself altogether. That is not correct, and we see that there is still a cycle. So that's not correct, right? That's why we have to remove this edge only. So we just get the two candidates, right? We get the two candidates and we check for both the candidates by removing, if we remove this candidate, then is there a cycle? If there is a cycle, then the other candidate needs to be removed, right? And if we again do the same thing, and that's how we are going to solve. So we are going to get the two candidates, check for the cycle using one candidate, and return, whichever gives a cycle, right? Whichever gives a cycle, then that is the node we return, because that is the edge we return, because that's why that's the edge is that is causing problem, right? So that's how we are going to solve this. And how we are going to detect a cycle, there are two ways. We can use a DFS or a DFS, or we can use a DSU. There's a union find data structure which we can use easily to find a cycle. So let's create a union find. Let's get into the code. I'll create the union find data structure first. Or actually, let me just do things, you know, uh, in order. Let's get the in degrees and the two candidates using those in degrees. So my in degree will be, initially it will be -1. What will be the size? Size will be edges dot size, because edges dot length is equal to n, right? Because we have one extra edge. Usually, what is the uh, relation between nodes and edges? This one. Or we can call this V also vertices. This is the usual relation, but since we have one extra edge, so this uh, one gets cancelled, so this is equal. That's how we have the constraints as well. So we can straight away get the edges dot size as the number of nodes, and we traverse the edges vector. If the in degrees, let me call this in degree instead, in degrees. Here, if in degrees of edges of I and 1, -1 I'm doing because I'm having edges dot size as a size, rate, so index will start from 0. So nodes have values 1, 2, 3. So this will be always 1, 2, 3, right? So I don't want it to go beyond the bounds. That's why I'm doing a -1. If it's not equal to -1, then I have already an degree for this one. So I will have two variables, or the two candidates. I'll call it A. Initially it will be -1, -1. And in this one, I'll store the index of the edge. That is that that will keep track of the two candidates by the end of this loop. So A is equal to I and B is equal to this one, uh, whatever is currently in this one. And if it is not -1, then I'll store I here. So now by the end of this loop, I will have A and B as the two candidates, and these two candidates will be, uh, you know, the two will be used for creating a DSU. First, I will try to not use A when creating a DSU. So, how we create a DSU? What we do in a DSU, we basically say, suppose this one has a cycle, right? DSU is basically used for directed acyclic graph rate, and it is used for detecting cycles because it's used for acyclic graphs. So it should not have a cycle. If it is, then it will tell us if it's having a cycle or not. So basically, 1, 2, 3, 4, 5. We get first edge 1, 2. So we add 2 here. If we get 2, 3, we add 2, 3 here. As of now, no cycle. 3, 4, no cycle. 4, 4, 1. Yeah, there's a cycle. Because 4, 1 is already connected, we get a cycle here. And this is the node. This is the edge that we need to remove. So that's how we do that. And for that, we have to create a union find data structure. So this is our usual template that I follow. You can follow whichever template you're comfortable with. I think there's not much of a difference in the other templates as well. The parent will be my vector for storing the parents, the pointer to the parent, and we'll have a rank. This rank will be initialized in the constructor, right? This will take the number of components that we have, and with that we run a loop from 0 till I is less than equal to n. I'm doing equal to n because we have node values starting from 1, so you can do it from 1 as well. I don't think that will be a problem. So let's do it like this. And actually, no, this one should be 0. Why 0? Because I will be pushing it, right? So I need a extra push for the 0th index as well. That's why. Parent dot push back. Here I will push I because initially each node is pointing to itself. So it's something like this. 1 is, 2 is like this. So each of them is pointing to itself. And for rank, I can have either 0 initialized to 0 or initialized to 1. So either of them is fine. I'll initialize it to 0. Alright, so this is my data structure. This is my constructor. My other function that I require is find parent. I'll pass the node to it, and I want the parent of this value. So I'll have something like parent of n, while P is not equal to parent of P. In that case, I want P to be equal to find parent of parent. I'll do it uh, like 2 cycles like this. So this will reduce the time complexity to close to O of 1. There's some factor alpha 1 or something. O of alpha, I'm not really sure, but it is almost equal to 1 if we use this along with the rank format. So I'll do that and I'll return P at the end if it's whenever it's equal. So actually this should be P. So parent of P of parent and find parent. Yeah, that's good. Here if we the next thing we need is the union function. So I'll call it unionize because union is a keyword I think in C++. I'll pass two child to it and I'll find the parent using the other function. If n1 if p1 and p2 are equal, in that case I'll return true because I have that node and I'm encountering it twice, that's why it's a cycle. So if p1 equal to p2, in that case I return true. So this is a cycle. Otherwise I will check the rank. If rank of p1 is greater than rank of p2, in that case parent of p2 is equal to p1. And similarly, if it's the other way around, then parent of p1 is p2. Otherwise, I'll just take either of them as the parent. Uh, I'll take p1 as the parent, and I'll increase the rank in this case because both of them have equal ranks. That's why I'll take p1 and I'll increase its rank by 1 and I'll return false since this was not a cycle. Now that I have a union data structure, I'll create a union find pointer which will point to a new data structure called union find. This will be the constructor and I'll pass edges.size. Right, and I will traverse the edges and I will check if A is equal to minus, A is equal to I. In that case, I won't take this as the first case. And if now I'll do the unionize function, I'll use it like this. Unionize of edges of I is equal to, sorry, edges of 0 comma edges of I 1. This is the edge that I pass as the two child, and if it is equal, in that case I have found a cycle. So if I remove A and I find a cycle, in that case I should return B, right? Because I have B in the cycle and that should have been removed so that we don't have a cycle. But the scenario where this is the case, at this point, since this one won't give me this scenario. So A and B will be -1 by the end of this loop because all of them have one edge, one incoming edge, right? All of them has one incoming edge. So if that is the case, then I have to remove only one edge that is possible, and that can be, here. That is this one. Edges of I is the edge that we need to remove. So in that case, if E is equal to -1, then I return edges of I, else I return edges of B, otherwise I return outside this loop, which means uh, this does not give me a cycle, right? So which means this is the edge which would give me a cycle. So in that case, edges of A I need to remove. Let's see if this works. There should be parent. Uh, adjust the size. Let's see this one. This one should not be a problem. Why is this? Oh, this should not be vector of n. Why is this? This should be vector of n. That's it. Unifying edges dot size. This should be a public all of these functions and members. Let's see what's the problem now. There should be one. There should be one. There should be one. So a lot of silly mistakes. Let's see if this works now. It does. The type complexity will be O of n because because the unionize function is close to O of 1 and we are doing it for each edge and probably it will be O of 2n, but that is equivalent to O of n, and the space complexity will be O of n again. And that's it. Thanks.